Hello everyone. This lecture video includes how to calculate the speed of sound in dry air as temperature changes and find the wave speed of a wave in the cable when mass, length, and tension of a cable are given. Let's look at the questions in detail. Question number 1 gives the length and mass of a steel cable, which are 29 meter and 2.5 kilogram, is stretched by the tension force of 56 Newton. What is the wave speed of a wave in the cable? The wave speed of a wave can be calculated from a formula V equals to square root of tension force T over mu. And T is the tension of a string depending on how tight the string is, and mu is the mass density defined in 1D, which is calculated from mass over the length of a string. Higher tension gives greater stiffness of material, and as they are strongly connected, this makes the wave speeds to be increased. Also, as the material is denser, it requires more energies to propagate, and this makes wave speeds to be decreased. To find the wave speed in meter per second, we should plug in all the values in SI units, which are meter, kilogram, and Newton, like given values. Let's plug it in to find the wave speed. The V equals to square root of tension force, which is 56.0 Newton, and mass density is 2.5 kilogram over 29 meter. That is calculated as 25.5 meter per second. The keynote here to remember is we can further use this wave speed to find frequency or wavelength of wave using V equals to lambda frequency. Now, let's look at question number 2. The speed of sound in dry air at atmospheric pressure and 0 degrees Celsius is 331 meter per second. Find the speed of sound in dry air at atmospheric pressure at 30 degrees Celsius. So pressure stays the same and the temperature increased by 30 degrees Celsius. In gases, sound travels faster at higher temperature, and the speed of sound is directly proportional to the square root of temperature. Also, just like the previous question, as density of material increases, it requires more energies to move, which reduces the wave speed of the material. So, sound speed is proportional to also square root of 1 over rho, which is square root of inverse of density. And thinking of an ideal gas situation, we can find the relationship between the density and temperature using the ideal gas equation, that is PV equals to nRT, and we can rearrange this equation to N over V, that is equals to P over RT, and we can multiply molar mass to the both sides of the equation. That molar mass is the ratio of mass over moles, which you can write mass in gram over N, where N is number of mole. So we can change that molar mass to the mass over N, and we can cancel these two N's. What we have on the left side of the equation is mass over volume, which is density, that is pressure over RT times molar mass. And this is a density equation. As you can see, from this density equation, density and temperature have inverse relationship that makes 1 over rho that is proportional to the temperature. So we can have this relationship that speed of the sound is proportional to the temperature. Now we can use the ratio equation of those two conditions to find the speed of sound at 30 degrees Celsius. So V, speed of the sound at 30 degrees Celsius over speed of the sound at 0 degrees Celsius is equals to square root of temperature at 30 degrees Celsius over temperature at 0 degrees Celsius. The speed of the sound at 30 degrees Celsius is equals to square root of T at the 30 over T at the 0 degrees Celsius times speed of the sound at 0 degrees Celsius. Now let's substitute in to find the speed. The key note to remember is for the temperature, we are not comparing the difference of the temperature, so we cannot use the degrees Celsius and need to change it into Kelvin by adding 273.15 from the degree value. So that is square root of 303.15 Kelvin over 273.15 Kelvin times 331 meter per second. That is equals to 349 meter per second to the nearest meter per second. Thank you very much for watching the video, and have a nice day.